Okay, so where are we? We are analyzing vacuum Maxwell's equations, and we saw several videos ago that these were the important equations from Maxwell's equations if we look for solutions in vacuum. And we're looking for solutions in which there's an EY and a BZ that depend on x and time. And these are going to describe plane waves rolling through the room in this direction. And on the previous two videos, we saw that these two equations imply these two equations. In particular, from Faraday's law, we got this equation, and from Ampere-Maxwell, we got this equation. Which is to say that if there is any vacuum solution to Maxwell's equations, which has the characteristics that we're looking for, where there's an EY that depends on x and t and a BZ that depends on x and t, and they describe plane waves, if there is a solution like that, it has to be that the EY and the BZ satisfy these two equations. And I want now to analyze these two equations together. So I want to simplify these equations in the sense that I want to find an equation which I'm going to end up with over here, which is only an equation for EY, and then an equation which is going to end up over here somewhere, which will only be an equation for BZ. How am I going to do that? Well, I have to somehow, first of all, I have to get rid of BZ. I have d by dt of BZ here and d by dx of BZ there. How can I combine them to get rid of the BZs? Well, the trick is to say, let me d by dx this equation, and let me d by dt this equation. And then the BZ terms are going to look the same, and I can eliminate them. So let's just do that. So I'm going to take this equation, and over here, I'm going to d by dx both sides. And what will I get? Well, I'm going to get that the second derivative with respect to x of EY is equal to minus d by dx d by dt of BZ. And then I'm going to, from this equation over here, I'm going to pull down this equation this way, but I'm going to d by dt both sides of this equation. And when I d by dt both sides of this equation, well, when I d by dt the left side, I get minus d by dt of d by dx of BZ. And if this were a math class, we would spend some time discussing why it's legal to switch the order of the d by dx and d by dt. This is a physics class, so I'm just going to say it's legal. We're going to do it. So d by dx of d by dt of BZ is the same thing as d by dt of d by dx of BZ. So when I take this equation and d by dt it, what I get on the left-hand side is exactly what I've already written. And so then I set that equal to mu naught epsilon naught d by dt of this, so it's d squared by dt squared of EY. And then I can simplify this and put a box around it by eliminating this term in the middle. So I get an equation which is an equation only for EY, and it looks like this. D squared by dx squared of EY is equal to mu naught epsilon naught d squared by dt squared of EY. And this gets a box. So I have simplified my life by taking two equations and combining them to get one. I've simplified my life by taking equations that have EYs and BZs in them and getting an equation that has only EYs in it. And I've complicated my life by taking first-order differential equations and getting a second-order differential equation. Before we start thinking about this equation, let's do the parallel trick, which is to say, let's start with this equation, and instead of d by dxing it, let's d by dt it. And let's start with this equation, and instead of d by dting it, let's d by dx it. And when I do that, what's going to happen is I'm going to have a d by dt of d by dx of EY, and I'm going to have a d by dx of d by dt of EY. And again, flipping the order of the derivatives, those are going to be the same. So let's do this, and let's start here. And in fact, I'm going to start on this side. So if I d by dt this equation, and I'm going to write the right-hand side of it first, that gives me minus d squared by dt squared of bz. And I'm d by dt'ing it, so here I have d by dt of d by dx of ey. D by dt, d by dx of ey. And, well, here I have d by dx, so I'm going to have d by dx of d by dt of ey. And that is going to be equal to what I get by d by dxing this side, but I have to bring the mu naught epsilon naught over. So I'm going to have 1 over mu naught epsilon naught, and then I have this minus sign. So in fact, there's a minus 1 here. And then what I have is d squared by dx squared of bz. And so eliminating this term in the middle and writing it out nicely and putting a box around it, and I also notice this minus is going to cancel that minus. I have d squared by dt squared of bz is equal to 1 over mu naught epsilon naught d squared by dx squared of bz. And I can put a box around it. And then I look at these two and I go, wait a minute, wait. Why is this mu naught epsilon naught upstairs and this one is downstairs? They look so similar. But then I realize, actually, here I have the d by dx squared term on the left, and here I have the d by dt squared term on the left. So I can actually rewrite this one to make it look incredibly similar to this one if I decide that I'm going to write it with the d squared by dx squared term on the left. So I'm going to write d squared by dx squared of bz is equal to, and that means the mu naught epsilon naught goes upstairs when it comes over here. And so I get a mu naught epsilon naught d squared by dt squared of bz. And this can go in the box also. So what have we done? We've started with two equations up here that had EYs and BZs mixed together. They both occur in both equations. They were both first order and derivatives, but they mixed up the EYs and BZs. And by this little calculus trick, I have gotten two new equations. This one is an equation just for EY. This one is an equation just for BZ. Yes, it's true they're second order differential equations, but I've now separated the EYs over here and the BZs over there. And the conclusion is that if we can find EYs and BZs that satisfy this equation and this equation, then we will have a solution to vacuum Maxwell's equations. It's going to satisfy both Faraday and Ampere-Maxwell. It's going to describe these plane waves with these planes where EY or BZ take on certain values rolling through space in the x direction. All we have to do is find an EY that satisfies this and a BZ that satisfies this, and you'll see that the two equations have the same form, so that tells us that EY and BZ are going to have the same shape and the same characteristics. And some small fraction of you may have seen equations like this before, and if you've seen them, you will immediately know that these are what are called wave equations. And for the large majority of you who are seeing equations like this for the very first time, what we're going to do in the next video is we're going to see that this describes waves. And this describes waves. So we are going to see that starting from Maxwell's equations, we have come to the conclusion that Maxwell's equations have hidden in them solutions in vacuum. No charges, no currents, just electric and magnetic fields, their dynamics in vacuum, satisfying wave equations and describing plane waves propagating through space. And this sort of concludes the journey that we started out on at the very beginning of 802. The beginning of 802, one of the first things I said was that one of the things that's going to happen to you as you go through 802 is that you will start out thinking about forces between charges, Coulomb's law. But by a certain point in 802, you'll realize that actually the interesting actors on the stage are not the charges and not the forces between charges, but they're the electric and magnetic fields themselves, that they will take on a life of their own, they will have a dynamics, they will do stuff on their own. And that is indeed where we are now. We have equations for electric and magnetic fields, no charges, no currents anywhere in town. And these equations have interesting solutions. They describe electromagnetic waves traveling through space. And in fact, we're going to see that what they describe is light.